All right, let's continue our discussion of graphs and digraphs. One reason it's worth pointing this out is because sometimes you have algorithms for graphs and you might wonder, well, is there a corresponding algorithm for digraphs? And vice versa, you might have an algorithm that does something concerning digraphs and you want to know a corresponding idea for graphs. So sometimes to help you think that through, it's useful to, like I said, realize that every graph corresponds to a particular digraph. Yeah, the shortest path problem is a good example. We've discussed the shortest path problem for graphs. And, clearly there's also an analogous shortest directed path problem for digraphs. Okay, given two vertices in a digraph, you'd like to know the shortest possible path, directed path, to get from the first vertex to the second vertex. Okay, now, I used the word subgraph previously when we were talking about connected components. Let's officially introduce the idea of a subgraph of a graph. So I'm moving back to discussing ordinary graphs, not directed graphs here. But what I say about ordinary graphs can be then translated into corresponding idea about directed graphs. All right, let's stick with ordinary graphs. So what do we mean by a subgraph of a graph? Well, a connected component would be an example, but the idea of a subgraph is far more general than that, right? The idea of a subgraph is you would take a subset of the vertices, so you would include some of the vertices of the original graph, possibly all of the vertices, but not necessarily, okay? You would take some of the vertices, and you would also take some of the edges, okay? But there is a restriction. The edges that you use, the edges that you select to take here, have to connect vertices that you selected also, okay? As long as you stick to that plan and as long as you stick to that restriction there, you select some of the vertices, you select some of the edges, but you make sure that the edges you select connect selected vertices. Then what you have produced is a subgraph of the original graph. Okay? So, as an example, let's consider the graph whose vertices are A, B, C, D, E, F, G, and whose edges are these ones right here. One of the subgraphs of that graph consists of the vertices B, C, D, E, and the edges B, C, and BD. Okay, so the subgraph has 4 vertices in it and only has 2 edges in it, and clearly the subgraph is not connected, right? The subgraph has vertices B, C, D, E, but there is no edge in the subgraph that can get you from E to E, right? Okay. But nevertheless, that's a perfectly valid subgraph. It doesn't have to be connected. And furthermore, it doesn't have to use up all the possible edges that connect the selected vertices. Yeah, so for example, right here, we selected, for the subgraph, we selected the vertices B, C, D, and E. Now, in the original graph, there's edge connecting C to D. But we did not select it for this subgraph, okay? You might think that it would be automatically part of the subgraph. It is not automatically part of the subgraph. So I say, this subgraph is not connected. Neither does it use up all the edges that it could possibly use among the selected vertices. So this idea of a subgraph, it's really quite general. The only restriction being that selected edges have to connect selected vertices. So subgraphs are pretty general, yet sometimes we want to focus in on subgraphs that are more, that have special properties. Okay, so there's some adjectives that are applied to certain types of subgraphs. One of the important types of subgraph is called a spanning subgraph. Okay, so what is a spanning subgraph? The answer is very simple. A subgraph is spanning if it includes all the vertices of the original graph. That's all it is. A more subtle idea is the idea of an induced subgraph. So when is a subgraph an induced subgraph? And the answer is it's induced if it uses all of the edges from the original graph that connect selected vertices for the subgraph. Okay, this is the very thing I was pointing out was absent in our example of a subgraph a moment ago. Our example of subgraph a moment ago was not spanning and it was not induced. Okay? It was not spanning, it didn't use all the vertices. And the reason it wasn't induced is because there are two vertices, I believe they were C and D, but don't quote me. But there were two vertices in that subgraph that we did not include the edge between those, even though there was such an edge in the original graph. Okay? Yeah, so it's not, that example was not spanning because it did not include the vertices A, F, and G. And that example was not induced because even though it did include the vertices C and D, it did not include the edge that connects C and D, right? I think if we toss that edge in, it would become an induced subgraph. You have to go back and actually check to see if there are any other cases of edges that were omitted. And now we say, well, we got two types of subgraphs. Induced, we have two special types of subgraphs, induced subgraphs and spanning subgraphs. What's the overlap between these? What would be an induced spanning graph? Well, in order to be spanning, it would have to use all the vertices. But then in order to be induced, it would have to use all of the edges. So there really is just one induced spanning subgraph of a graph, and that is the original graph itself. The original graph is a subgraph of itself. So now here's another special type of subgraph that is quite important in graph theory and quite important in a lot of practical problems. Okay, so we say that a subgraph, well, first of all, we'll say that a graph is a cycle if it's connected and if every vertex is adjacent with exactly two other vertices. Okay? This is a picture of a cycle, a graph that is a cycle, right? There are four vertices, and each vertex is adjacent to two others. And furthermore, this is a connected graph, okay? Well, the only way that can happen is if you get something that's cyclic looking, you know, like this right here, okay? So such a graph is said to be a cycle. So now, if we start with any old graph, okay, begin with any old graph, it's particularly interesting, useful to wonder about subgraphs that are cycles, okay? So we would say that a subgraph is a cyclic subgraph if that subgraph is a cycle, okay? And, you know, the cycles inside a graph figure into graph theory in lots of interesting ways. But the most fundamental thing we can ask about a graph is, does it or doesn't it contain a subgraph that is a cycle? Okay? If a graph does not contain any cyclic subgraphs, then we say that the graph is acyclic, right? A graph is acyclic if you can't find any cycles inside it. Yeah, and that's a very, very special type of graph. Okay? So I say again, it's called an acyclic graph. And there's another name given to it commonly that will make sense in a moment probably, but acyclic graphs are also called forests. The reason that name makes sense is because of especially great importance are graphs that are acyclic and also connected. Yeah. So if a graph is connected and it doesn't have any cycles in it, we say that that graph is a tree. Aha. Well, that's interesting. We've been using that word tree for some time now. In talking about data structures, in particular when we studied heaps and we studied binary search trees, we had the notion of a binary tree. Yeah. Well, here in graph theory is an idea that generalizes that. Okay? A binary tree is really a special case of a tree. Okay? What is a tree? A tree is a graph that is connected and it's acyclic. I should have a picture of that. But in any case, now let's consider again an arbitrary graph. Okay. We want to introduce a notion of a spanning forest. So the definition of a spanning forest for a particular graph is that it's a subgraph and that it's spanning and that it's acyclic. Okay? This is a lot of stuff that's hard to get your head around without pictures. But let's see what we can do here. So we're thinking about a graph to begin with, and we're thinking about a spanning subgraph, so it has to use up all the vertices, and furthermore, the subgraph is not allowed to have any cycles in it, okay? If we have such a thing, then that subgraph is called a spanning forest. If it happens to be connected, and that would happen if and only if the original graph is connected, then the spanning forest is said to be a spanning tree. Okay? It's a very important idea, spanning tree. So let's see what we can do to start visualizing some of this. Okay, say we start with this graph. This is clearly a connected graph. So it makes sense to talk about a spanning tree for this graph. And here is a picture of a spanning tree for the graph we were just looking at. So you notice that a couple things. It uses up all of the vertices, right? And secondly, it's acyclic. There are no cycles in this. In the original graph that we looked at in the previous slide, there was a cycle. Go back and see if you can't find it, right? We took a lot of the edges here, but we avoided putting in too many edges, right? We avoided putting in edges if they would cause a cycle to occur. So that's a spanning subgraph that's acyclic. That is a spanning tree. If the original graph had not been connected, then of course we couldn't get a spanning tree, but we could still get a spanning forest. Each connected component, we'd get a spanning tree for each connected component. You put them together and you have a spanning forest. Okay, so say you start with this graph that we looked at previously. It has a cycle. A, B, and C, the subgraph, the induced subgraph, using vertices A, B, and C, consists of the vertices A, B, C, and the edges between them. That is a cycle, right? That's a cycle. Okay, well, therefore, this cannot be a forest, right? This cannot be an acyclic. This is not an acyclic graph. But here is a subgraph that is both spanning and acyclic, and therefore this is a spanning forest for the original graph. Okay, before we go on to part B of these lectures, this lecture on graphs and digraphs, go over all of this again just to double check that you understand the terminology, the concepts and the terminology. Okay, we'll be getting involved with, some practical applications of graphs a little bit and thinking about algorithms for solving questions concerning graphs. So before doing that, it's important that we have the agreed upon language. We should understand what a subgraph is, acyclic subgraph, spanning subgraph, induced subgraph, those kinds of things.